Now, moving ahead to question number 13. It is based on Brayton cycle. So here we are discussing that an ideal Brayton cycle operates between the maximum temperature and minimum temperature, that is T3 and T1, okay, respectively. For constant values of T3 and T1, the pressure ratio for the maximum work output is. So that means we have to find out for the constant value of T3 and T1, the pressure ratio for the maximum work output. Okay, that means we have to find out कि हमारा maximum work output कहाँ निकल रहा है when we have fixed the upper limit and the lower limit of the temperature. So let's just draw the TS diagram for the Brayton cycle first. So it is T and S. So first process is isentropic compression. Then we have this, again this and this constant pressure heat rejection. Take care. So it is 1, 2, 3 and 4. So this T3 is the maximum temperature and T1 is the minimum temperature. That means we have fixed this T1 and T3. All we can change is these temperatures, that is T2 and T4, in order to get different pressure ratios and different work output. Now, we know that the maximum work output we'll achieve when this behaves like an ideal heat engine or for a gas. That means हम लोगों का जब कार्नोट साइकिल की तरह behave करने लगेगा, then in that case we'll achieve the maximum work output. Now, for maximum efficiency, right? But we need to find out maximum work output, that is the optimum work output. So for that we have the work net. That means the work net will be equal to work done by the turbine minus work done by the compressor. Here we have the work done by the turbine, here we have the compressor, right? So work done by the turbine would be equal to Cp. MCP, we are considering mass of 1 kg over here. So work done by the turbine would be T3 minus ka T4 minus the Cp. Work done on the compressor would be equal to T2 minus ka T1. So we'll be getting this. Now T3 and T1 are constant. So what we can do, if it is an ideal case that is given, so then in that case, we can say that T2 by T1 would be equal to T3 by T4, right? And because T3 and T1 are fixed, then in that case, we are replacing this T4 by T in terms of this. So T4 would be equal to T1 into T3 by T2, and we'll be replacing it over here. That means we can alter T2 and T4, but दोनों variables को इकट्ठे नहीं हम लोग modify कर सकते. Therefore, I have replaced this T4 in terms of T2. So work net would become Cp T3 minus ka T4, that is T1 minus ka T3 divided by T2 minus ka T2 plus ka T1. We're getting this. Now work net maximum हमारा तब होगा, we'll just differentiate this work net with respect to dt2, and we'll be getting T3 is constant, so it will be 0 minus plus हो जाएगा हमारा, we are differentiating in terms of T2, that is T2 square minus 1 and plus का 0. So now this work net अगर हम लोग differentiate करेंगे, if it is equals to 0, then in that case this work net is maximum, right? So it will be maximum if it is equals to 0. So that means T2 will be equal to under root T1 by T3, right? So we'll be getting the maximum work net from here. So but we don't have to find out the maximum work net, right? We have to find out the pressure ratio. So the relation between T2 and T3 is known. So what we can do is we can find out the pressure ratio. Now the pressure ratio for this would be P2 by P1, right? And because 1 to 2 is an adiabatic process or is an isentropic process, then in that case we'll be using the expression that is T2 by T1 will be equal to P2 by P1 whole to the power gamma minus 1 upon gamma. So if we are to find out P2 by P1, then this will be equal to T2 by T1 whole to the power gamma upon gamma minus 1. So T2 by T1 है हमारा, T2 को we can replace in terms of T3 because हमारा जो expression है that is in terms of T3 and T1. So RP would be equal to it will be under root T1 by T3. So हमारा आ जाएगा under root T3 by T1 whole to the power gamma upon gamma minus 1. We can write it as T3 by T1 whole to the power gamma upon 2 times gamma minus 1. That means option C. Option C is the right answer because T3 by T1 whole to the power gamma upon 2 to the power gamma minus 1 would be the answer for the optimum pressure ratio at which the work maximum हम लोगों को मिलेगा. Now, moving ahead, we are going to read question number 14. That is, a heat engine receives heat at 1000 Kelvin and rejects to the environment at 300 Kelvin. The efficiency of the heat engine is half as that of the efficiency of the Carnot engine operating between the above method mentioned temperature limits. Okay. Now, the work output from the heat engine is completely used to drive a refrigerator that steadily removes the heat from a cold place at the rate of this and rejects the heat to 300 Kelvin. The COP of the refrigerator is half of the COP of the Carnot refrigerator operating between the same temperature limits. Now we have to find out the rate of heat supplied to the heat engine. Rate of heat supplied to the heat engine is in kilowatts. We have to find out. So let's just draw the schematic diagram first for the heat engine. हीट इंजन है. सो हीट इंजन हमारा वर्क प्रोड्यूस कर रहा है. दिस इज एट 1000 केल्विन एंड दिस इज एट 300 केल्विन. फाइन. सो द एफिशिएंसी, सबसे पहले इसकी एफिशिएंसी हम लोग कार्नोट साइकिल के बीच की निकाल लेंगे. सो द कार्नोट साइकिल की एफिशिएंसी इफ वी आर टॉकिंग अबाउट इट विल बी इक्वल टू 1 minus TL by TH, right? So this TL is 300 and this TH is 1000. So it will be 0.7. Yes. Yeah. I mean, how we can find it out? We will find it out by 1 minus 300 divided by 1000. It will come out to be 0.7. Now, the actual efficiency of this heat engine would be half of that of the Carnot cycle. So it will be 0.7 divided by 2, that is 0.35. Now this heat engine is used to derive the refrigerator. This is the heat engine and this is the refrigerator that operates between 260 Kelvin and 300 Kelvin. Okay, so let's just say ये हमारा connected है. This is also 300 Kelvin and ये हमारा हो जाएगा. Okay, this is 260 Kelvin. यहाँ से हमारा heat remove करेंगे and here हम लोग work is given. Now, it works on this rate that steadily removes a heat of 5.2 kilowatt from this and rejects the heat to the same environment, that is at 300 kilopascal. Fine. Okay. And what we have to find out, the rate of heat supplied to the heat engine. That means we have to find out Q. The amount of heat that is being supplied to the heat engine from the source, we have to find out Q. So for that we need to find out work done. So work done अगर हम लोग निकाल लेते हैं और let's just talk about the heat engine first. Heat engine का efficiency we have found, that is 0.35 and work done efficiency would be equal to work done divided by Q provided. So work done we can find out and this will be equal to work divided by 0.35 would be equal to the heat being supplied to it. Fine. So first we have to find out the work done. Work done हम लोग रेफ्रिजरेटर के केस में फाइंड आउट करेंगे बिकॉज हम लोगों का जो कार्नोट रेफ्रिजरेटर का COP है उसका हाफ होगा एक्चुअल COP. सो फर्स्ट वी हैव टू फाइंड आउट द COP फॉर कार्नोट रेफ्रिजरेटर. कार्नोट रेफ्रिजरेटर का COP हो जाएगा हमारा desired effect divided by desired effect divided by the input. So हम लोग कर रहे हैं, that means desired effect is 260 kelvins because we are talking about Carnot. So 260 divided by 300 minus का 260, that is 260 divided by 40. Yeah, it will be 260 divided by 40 and that will be 6.5. So 6.5 is the COP of the Carnot refrigerator, but the actual COP would be half of this. That means 6.5 divided by 2, that is 3.25. Now, COP of refrigerator is 3.25, and this COP would be equal to the heat rejected, that is the desired effect. So I'm just writing desired effect over here, divided by the work done on it. So that is 5.2 divided by work done. So we can find out the work done would be equal to 5.2 divided by 3.25, and this would be equal to 5.2 divided by 3.25, and this will be equal to 1.6 kilowatt. Now 1.6, we have to find out Q ultimately, and we have found the work done. So Q would be equal to 1.6 divided by 0.35, 1.6 divided by 0.35, and on solving we'll be getting it to be 4.5714 kilowatts. That means the heat being supplied to the heat engine from the source is 4.5714, that is 4.5714 kilowatt. Coming to question number 15, it says a room contains air at 25 degrees Celsius, 100 kilopascals, and 80% relative humidity. If the saturation pressure of water at 25 degrees Celsius is this, then the specific humidity we have to find out. That means we have to find out the specific humidity. Saturation pressure de rakha hai, that means the PV is given already. So initially, agar we are talking about the relative humidity, the relative humidity would be equal to PV by PVS, right? So saturation vapor pressure at 25 degrees Celsius is also already given. So we can do is 0.8 would be equal to PV divided by 3.1698. Hence, PV would be equal to 0.8 times of 3.16, and that will be 2.5354 kilopascals. That means partial pressure of water vapor at 25 degrees Celsius is 2.534 kilopascal. Now we have to find out the specific humidity. Specific humidity is equal to 0.622 multiplied by PV divided by PT minus ka PV. So just we have to put the value of PV and PT over here. PV we have found, that is 2.5354. Total pressure is given to be 100 minus the 2.5354, and ultimately the specific humidity will come 0.0161 kgs water vapor divided by kgs per air. That means this is the specific humidity that we are getting, 0.0161 would be the answer. Coming to question number 16, it says an insulated rigid container is divided into two parts by a thin partition. Okay, one part contains 6 kg of the saturated liquid vapor mixture with the dryness fraction of this. Okay, the other part is saturated liquid at 0.6 megapascal. When the partition is removed, the system attains equilibrium, the final specific volume of the mixture. That means initially we had two parts in this box. यहाँ पे हमारा liquid plus vapor mixture था, and here we had only liquid that was at 0.6 megapascal, and this air mixture, this gaseous liquid vapor mixture was 0.3 at 0.3 megapascal with dryness fraction as 0.7. Okay, so what we can do is we have to find out the final specific volume of the mixture. Okay, so first of all, we have to find out the specific volume of this side and this side. So I'm writing part 1 and part 2. So we'll be discussing about part 1 first. So the specific volume for the part 1 would be, we have 6 kgs of this. Okay, but before we can find out, we have to find out the actual specific volume of part 1, that will be equal to V. Writing it at V1 will be equal to Vf plus X times, which is already given, the quality is given to be 0.7 Vg minus ka Vf, right? Because it is at 0.3 megapascal, so we'll be using these values over here and putting it. So V1 हमारा हो जाएगा VF that is 0.001073 plus का 0.7 multiplied by VG that is 0.60582 minus का 0.001073. ठीक है. On solving value of V1 that is the specific volume in case of 1, it will be 0.4243 meter cube per kg. And the total volume would be, because हमारा mass दे रखा है that is 6 kgs. So what we can do is we can multiply this 0.4243 by 6 and we'll be getting the total volume. That means the total volume of the first will be equal to 0.4243 multiplied by 6 and that will be equal to 2.5458 meter cube. Okay, yeah. Now coming to the second part. Second part may we have saturated liquid, 12 kgs of saturated liquid, and this 12 kg of saturated liquid is at 0.6 megapascal. So the total volume of the second one would be 12 kg multiplied by specific volume of the saturated liquid at 0.6. That means it is equals to this thing. So that will be equal to 12 multiplied by 0.001101 and it will be equal to 0.013212. Okay. Now we have to find out the specific volume of this entire mixture. So specific volume of this entire mixture would be equal to volume in first part plus volume in second part divided by the total mass. Total mass would be 6 plus 12, that is 18. That means the specific volume of this total mixture after the equilibrium would be equal to 2 point, यहाँ पे मीटर क्यूब हम लोगों का था, so it will be 2.5458 plus 0.0132 something divided by 18. So the total volume, specific volume of this expression would be 0.142 meter cubes per kg would be the answer for the specific volume of this entire mixture. Coming to question number 17. So question number 17, it says during a steady state air conditioning process, air enters a heating section at 15 degrees Celsius with 40% relative humidity and leaves at 30 degrees Celsius. Assuming the heating process takes place at 100 kilopascals, the relative humidity of the air at the exit. Let's just draw the block diagram first for a better understanding. यहाँ पे we are doing heating. Here 15 degrees Celsius, 40% RH and leaving at 30 degrees Celsius, and this entire process is being taking place at 100 kPa. Here we have to find out the relative humidity in the second case. Now at 15 degrees Celsius हम लोगों का saturation pressure दे रखा है, that is 1.7057, right? So the relative humidity, it is equals to PV by PVS. So it is 0.4. Partial pressure हम लोग निकाल सकते हैं यहाँ से, that would be 7057. So the partial pressure at 15 degrees Celsius for the water vapor, for the air that is moving in, it is equals to 0.4 multiplied by this, and it will come out to be 0.68228 kilopascals. Now we have to find out यहाँ इस वाले 30 डिग्री सेल्सियस पे हम लोग का पार्शियल प्रेशर दे रखा है, राइट? या ठीक है. Now on heating what happens, यहाँ पे no water is being removed, right? So and the total pressure also remains the same, only the temperature is changing and no water is being added or being removed. So the partial pressure of the vapor remains the same. Partial pressure of the vapor in this air remains the same. That means PV in this second state, that is the gas that is moving out from the heating section, will remain the same, that is 0.68228 kilopascals. And हम लोग यहाँ पे relative humidity निकाल सकते हैं, that will be equal to PV by PVS at 30 degrees Celsius, because we are talking about 30 degrees Celsius. So the saturation vapor pressure would change, and here we have 0.68228 divided by PVS, that is the partial pressure of the vapor at saturated conditions at 30 degrees Celsius, and that is given as 4.2469. So what we can do is we'll divide these two equations, these two terms, and it will be 0.1606. अगर हम लोग इसको परसेंटेज के बारे में बात करें, that will be 16.06%. That means the relative humidity of the air that is coming out from the heating section is 16% approximately. So this would be the answer for this question.